when I go ahead and get started, and first of all, let me just share with you the activity that's scheduled for next week. So I'm going to change my screen here. And since it's an activity, you basically will have to fill it out in Canvas. But if you complete the worksheet, you should be good, because the worksheet should be mirrored by the content in Canvas. So in Canvas, some of the videos that I've done in the past, okay, I always want to put that out there, because this particular video won't be uploaded until probably tonight or tomorrow. So it tells you about what needs to happen, but you also get to see the activity by just clicking on that and doing a preview. Okay, and these are what's going to be in the Canvas that you have to fill in. So it pretty much tells you about Lewis structure, and then it talks to you about doing the molecular geometry, and then practice that, and then we will take you to a program called Chemdl, where you will see that the predicted structure that you created is actually what's in this model, and then you can get some properties. So that basically is the activity. So let me go ahead and get started here. Let me go back. So again, that's going to be in the information section, and that's found right here. Okay, and then this is what you guys are going to be completing. Now, this is a little bit tricky. Reason why it's tricky is because the way Canvas sets up the they're called quiz, even though in this particular case it's an activity. The way Canvas sets up these activities, or these questionnaires, is that you guys are going to fill it in directly. So let me do a preview. And under student view, let me see. Do this. So of course you have to put your ID and all that, and then you have these blanks here, and it kind of asks you, okay, number of bonds in NH3. So if you did it in your worksheet, you should be able to put a number right here, and then the number of lone pairs in NH3, you should be able to put a number here. And then you go to the next one, and you can see that that's pretty much similar to, just go over here. So here's ammonia, and then this is chloromethane and carbon disulfide, and then formic acid. So if you do that, and then that's essentially what you will see right here. Okay, you just complete it, and you will be able to determine the total valence electrons, the number of bonds, and then the lone pairs. And then this is the connectivity, and then you want to do the Lewis structure, because at the very end, you guys are going to have to upload this worksheet that you are doing onto Canvas. Okay, this worksheet that you're doing. So at the very last question here, you guys are going to be drawing the Lewis structure. Okay, so once you complete that, then there's part 2. And in part 2, it's a little bit more involved. Again, what you have here is, now these boxes corresponds to these questions right here, and you just put your answer. Write the letter in the answer box to designate A, B, C, or D. So in this question right here, okay, the Lewis structure and total valence electrons, well, this is going to be for, this should be for, let me just double check. Yeah, here. Carbon disulfide, okay? This up here is just the example, but this is carbon disulfide, this is carbon disulfide. And the question here is, when you complete the Lewis structure, which one is the correct Lewis structure? Okay, type the number of total valence electrons. So you want to type the number of total valence electrons in this particular case, and then type one of the following: the electronic designation, and then the geometry based on the electronic designation. And then number 5 is, based on the electronic designation, you're going to pick one of these. that corresponds to linear, trigonoplanar, tetrahedral, or some weird shape. So in the second part, you just go through these questions and put the answers in these boxes over here. Kind of similar to your activity on this part right here, okay? What you guys are going to be doing is right here, carbon disulfide. You guys are going to put the valence electrons, the AE designation, the geometry, and then the shape, and then the molecular geometry. And so that's basically what you are doing here. Okay, so that's the second part of your activity. And then the last part, so there's a bunch of questions like that, and each one is a separate question. The last part is this right here. Okay, this is the last part of your activity is this right here. And what you want to do is figure out the bond angle, the bond length, the partial charge, molecular geometry, and the bond dipole. Now, this is not something that you would figure out. It's something that you would look up. If you go to Chemdl, if you just click on that, it'll take you to a site, and it'll take you to this site. And all you've got to really do to answer these questions, okay, let me do one here. Let's do the nitrite ion. So go over here and just type nitrite ion. And when you do that, it'll find it for you in this library. You click on it, and then it'll give you the structure. So what you want to do, and you can use your mouse to move it, okay, freely, like that. You want to take a screenshot, okay, so that you can put it in your notebook. And then look at the questions here. The questions is the bond length. So if you go over here, you can actually, yeah, here's the screenshot right there. Okay, so you can paste that in the question right there. So the bond length would be right here. You click on that, and it'll tell you what the bond lengths are. Okay. The other question here is the bond angle and the partial charge. Let's take a look at that. The bond angle, it's right there. It's 115.7. And the partial charge is right here. It tells you, because this is a polar chemical, the negative tells you the polarity measures the degree of negative and positive. And so the degree of negative and positive is minus 0.6, minus 0.6, and 0.2 on these, okay? Molecular dipole, you can click that and you can show that that's the molecular dipole. Basically, the dipole is where the majority of the negative is if you were to draw a line. And then the bond dipole is the dipole per bond. So you have all that information in this Chemdl program. Okay, you have all that information. And it's good to be aware that there are information out there for you guys to use. This is glycine. Let's see if glycine is in there. Should be in there because I did write the lab manual, and I made sure that these chemicals are in the library. You know that glycine is a more complicated chemical. It's an amino acid. So this is it right here. Okay, so that basically is your activity, and you're going to fill it in Canvas. You're going to fill it in Canvas via these questions. And then, of course, you're also try and do it in your worksheet first, because you are going to have to take a picture of it anyway, and then upload it here. Okay, so like right here, for this particular page in your activity, you're going to have to upload it. So what we're going to be doing is just looking at Lewis structure. And Lewis structure is a way of representing the chemical structure based on its valence electrons. That is the electrons in the outermost shell. Okay, so let's take a look at this. And this is G.N. Lewis right here. But you can see right here, it talks about we're not going to be talking about ionic substance. That's not part of this discussion. Okay, what we are going to be talking about is molecules that are pure covalent or polar covalent. So we're not going to be talking about these chemicals because the way these things are structured, it's basically a matrix of alternating ions. It's not a single entity like water, or in this particular case, methane's right here. Okay, that's methane. So when you're doing Lewis structure, you have to remember the octet rule. The octet rule is a way to, it's the driving force for why molecules form. And the driving force for why molecules form is because the atoms that make up the molecule want to be stable. And sometimes you might say, well, aren't atoms stable anyway? Yes and no. Yes, they are stable because you can isolate them. So you can, these chemicals, you can isolate. So they are stable that way, but they want something to a higher, they want to be even more stable than that. And the way they do that is they negotiate their electrons. If it's got too much electrons, it sheds its electrons. So it has the same number of electrons as the closest noble gas. If it has too much, if it has too little electrons, then it tries to pull electrons from an atom that will sacrifice its electrons. And again, to get the same number of electrons as a noble gas. That's the key. So that's basically what the octet rule is. But there are exceptions. Unfortunately, in chemistry, we tell you the general trend, and then we renege on our promise because there are so many exceptions. Nature just likes to work that way. Transition metals, for example, they can have more than 8. And why do they do that? Because they can actually start using their d orbitals in order to form bonds or to have lone pairs. Okay, and any element like below the third row, the third, fourth, and fifth, because remember, the third shell is when the d orbital starts to form. You don't have a d orbital in the first shell. The only orbital you have is 1s. Second shell, you have 1s and 2p. Third shell, you have 1s, 2p, and 3d. Once you have the d orbitals available, then we can have something called valence shell expansion. And then you can also have compounds in which it doesn't need 8. Sometimes it's just happy with 4. Sometimes it's happy with 6, like boron and beryllium. Okay, but after boron and beryllium, these chemicals always want 8 electrons. Hydrogen is an exception to the octet rule. You can't put 8 electrons on hydrogen. It just won't fit. It only has that first shell that can be occupied. Okay, so the first shell can only fit 2 electrons. So whenever hydrogen makes a bond with another chemical, another atom, it's totally happy with 2. And we call that the duet rule, the duet rule. Anyway, the driving force for Lewis structure is the octet rule, with the caveat that hydrogen prefers 2. Okay, so here's examples of elements and how many valence electrons they have. The halogens have 7. By pairing this one unpaired electron, then pairing that, then it can form one bond with whatever atom is donating the other extra electron. Oxygen has 6. So by pairing these two, it can form 2 bonds. So I say here that the halogens often have just 1 bond, but again, there's the exception. Some halogens can have 3, some can have 6, okay? But fluorine definitely just wants 1, but these are the general rule. Nitrogen with its 3 unpaired, 3 bonds, and carbon with its 4 unpaired, 4 bonds. 99% of the carbon compounds have 4 bonds. There are a couple of exceptions. Carbon monoxide, for example, is satisfied with 3 bonds. Carbon disulfide is satisfied with 3 bonds. But for all other carbon-containing compounds, the carbon in those compounds prefer 4 bonds. Okay, so here are the examples of the exceptions. Whenever you have an odd number of electrons, see here, nitrogen comes in with 5, oxygen comes in with 6. This is going to be 11 electrons. You're never going to obey the octet rule. It's always going to violate the octet rule when you have an odd number of electrons. Now, if you have NO positive, then nitrogen comes in with 5, oxygen comes in with 6, but the positive there means that there's 1 electron that is lacking. The positive means you've got more protons than electron by 1. So you have to subtract 1 electron from the total, and you get 10 electrons for that compound, the valence electrons. So that can obey the octet rule. If you have nitrogen that is negative, then what you have here is you've got nitrogen with 5, oxygen with 6, but the negative tells you there's 1 extra electron. So you have to add 1 more, and that'll give you 12. And an even number of count will obey the octet rule. So when you have an odd number of electrons, it always violates the octet rule no matter what. But if it's charged so that it changed that odd to an even, then most likely it obeys the octet rule. Okay. Yes, there's a question? No? Okay. If you have questions, just unmute yourself and then you can just chime in. Then I told you about boron and beryllium, that they're happy with 4 and 6. Well, here's boron. It's got, whenever you see a line here, that represents 2 electrons. Okay, so boron is satisfied with 6 valence electrons. That's because it's small and it's early in the periodic table. These fluorines, however, are going to have 8. These fluorines are going to have 8. Okay, like this. And if you count the total number of electrons, there's 6 here. That's from the bonds. And then each fluorine has 6. 3 times 6. That's 18. 18 plus 6, that's 24. And if you think about it, each fluorine in the periodic table has 7 valence electrons. And there's 7 fluorine, so 7 times 3 is 21. And then boron has 3 electrons, so 3 plus 21 is 24. So you can see that what electrons each atom is bringing is equal to the total number of electrons in that structure. But it violates the octet rule. Okay, it violates the octet rule. So you just have to remember that boron and beryllium are going to have less than 8 electrons, as well as hydrogen, as I mentioned already. Okay, here's beryllium. It's got 4 valence electrons by sharing its 2 electrons with hydrogen. And then, like I said earlier, when you have elements in the 3rd period and lower, these chemicals right here are going to violate the octet rule because they start to use their d orbitals. Okay, so that's what valence shell expansion is. If you look at this iridium right here, it's got 2, 4, 6, 8, 10, 12. That's 12 electrons in its valence shell. Remember that when bonds form between atoms, they're using their outermost electrons, their valence electrons, because those are the ones that are going to make contact with the other atom. All these are going to be in violation of the octet rule, but for the most part, you guys are going to work with chemicals that does obey the octet rule. Okay, especially when it comes to human life. When you have human life, in terms of the molecules that make you and me, the molecules are going to be from the 2nd period, nitrogen, carbon, oxygen, okay? And those things always obey the octet rule with the few exceptions I talked about, okay? So the best way to do this exercise, one, determine the Lewis structure, and two, determine the molecular geometry, is through the technique that I've outlined in my lecture and that I'm going to outline here. There are other methods out there, and I find out that they can lead to mistakes because you're sort of guessing as to where the electrons belong. But using the bond table that I'm going to share with you here, you can definitely see how, using the idea of the octet rule, you get the correct Lewis structure. And once you have the correct Lewis structure, you can come up with the correct molecular geometry. Okay, so you need to know the connectivity. That's how the atoms are arranged in space and which atoms are going to be connected to what atoms. So you don't usually have that experience to know the connectivity for complicated chemicals. For simple chemicals, the connectivity is pretty straightforward. The first element in the formula is generally the central atom, except when that first element is hydrogen and fluorine, because hydrogen and fluorine can only form one bond. It can't have two, so it can never be central. What I mean by a central atom is that there's an atom that bonds to other atoms, 2 or 3 bonds, 2, 3, 4 bonds. So that's what we call a central atom, because it's going to be the center by which the other atoms anchor to it. If you can only form one bond, then that can't be a central atom, because you're going to be hanging out in a terminal and you can't continue that chain. So hydrogen and fluorine can never do that because they can only form one bond. All the other atoms can be central atoms. And then in this bond table, the most important thing that you can get is how many bonds in the structure. And this bond table will allow you to calculate that. And then how many lone pairs does that structure have? Because you have to account for all the total valence electrons that each atom brings to that structure. So by using this bond table, you'll get that answer right away. Okay, so let's do a simple chemical like carbon monoxide. Carbon monoxide, super easy. You can do this by inspection, because if you do the Lewis structure, you see that oxygen has 6. That's how you represent the electrons on the atom. You put it in the 4 corners, the top, the bottom, the left, and the right. You generally do that in terms of designating the electrons. And remember that the shell wants 8. So the top, bottom, left, and right, if you put 2 electrons apiece, that adds up to 8. Okay, so this is how I'm going to draw my oxygen. And then I'm just going to draw my carbon this way. Okay, and then what I'm going to do is I'm going to connect the electrons so that each atom has 8. Again, that's the octet rule. So these two will be shared. These two will be shared. And it looks like oxygen is happy, so it's not going to share anymore. But carbon is lacking 2 electrons. Okay, right now carbon has these, and that's a total of 6. So oxygen has to come in and donate those 2 pair of electrons in here. And when it does that, then this is basically what the Lewis structure will look like. And I'm going to use pen to designate the electrons on carbon. I mean, different colors to designate the electrons on carbon and the electrons on oxygen. So that's carbon monoxide. You see the green dots represents the electrons from oxygen, and the red X is the electrons from carbon. But that's a fairly simple molecule, and that you can see in this particular case, they definitely obey the octet rule. Here, this carbon has 8, that's 2, 4, 6, 8. This oxygen has 8, 2, 4, 6, 8. And you can count those electrons that are tying those 2 atoms together for both sides. Okay, you can do that. So, like I said, it's a simple chemical, but let me show you using the simple chemical how the bond table works. The way the bond table works is you calculate you set up a table like this, where you put the formula on the upper left corner, and then you break down the atoms in that formula, and then you put two more columns here, code OE. OE stands for octet electrons. Octet electrons tells you if the atom were to get a same number of electrons as a noble gas, how many total would be around that atom? And the answer is always 8, 8, or 2. And it's only 2 for hydrogens. It's 8 for all other atoms. Okay? So it's a simple thing to remember, but you guys are going to forget. Okay? It's always 8 or 2. This can only be 8 or 2. That's the octet electron. And then there's something called the total valence electron, and that's based on the periodic table. That's how many electrons each atom is bringing in based on its number of electrons for that particular atom. Carbon brings in 4. Oxygen brings in 6. That's found in the periodic table. Hydrogen brings in 1. Okay. Nitrogen brings in 5. Phosphorus brings in 5. Those are the valence electrons. So when you do this table, like I said, you use this column to the left to account for all the atoms in your chemical and the charge. Okay, carbon monoxide is not charged, so you don't have to worry about that in this example. And then you can see that the octet electrons for carbon is 8. The octet electrons for oxygen is 8. Again, how many total electrons are going to be in the outermost shell if it's going to have the same number of electrons as a noble gas? It's either 8 or 2. Don't make it harder than that. But in reality, based on the periodic table, carbon only has, and then we add it up, 4, and oxygen only has 6. So if you add that up, you're going to be dealing with 10 electrons in your structure. That's the reality. The magical thing about getting the octet electron and the total valence electron is that the difference between 16 and 10, this difference right here, 16 octet electron minus total valence electron, is the number of electrons you have to commit to the bonds. And then if you divide it by 2, that's the number of bonds. So 16 minus 10 is 6. That's the number of electrons you have to commit to the bonds. And then dividing it by 2 gives you 3 bonds. So that's what we're going to do. We're going to put the 2 atoms together, and we're just going to draw 3 lines, meaning 3 bonds, 6 electrons. Each line represents 2 electrons. Okay, those 3 lines represent 6. But now we only have 10 to deal with, and we've used up 6. That means that we have to account for the 4 more electrons we haven't used up yet. Well, those 4 remaining electrons are your valence, are your remaining electrons, and we can use that to count the number, see, 10 minus 6, the number of lone pairs. That's going to be the electrons not involved in bonding. So if you take 4 and divide by 2, because a lone pair is 2 electrons, you'll see that we have 2 lone pairs for this guy, and we do that by completing the octet. 2 on that oxygen, 2 on that carbon. Now we have 8 on carbon and 8 on oxygen, obeys the octet rule, and we account for all 10 electrons. That's the magic of the bond table, okay? It takes a little bit of work when you're first starting it, but once you get through it, you just fly through, okay? But again, I remind you right here, if you guys are going to make a mistake, you're going to make a mistake there, because the rest of these are pretty straightforward, okay? Let's go to something more difficult. Let's go to something more difficult. HCN. HCN is going to have hydrogen, carbon, and nitrogen. So octet electron, total valence electron, we account for all our atoms, H, C, and N. And then the octet electron column, 2, that's the connectivity. 2 for hydrogen. Remember, it's always 2 or 8. I can't stress that enough. It's always 2 or 8. 2 for hydrogen, 8 for everything else. So if all the elements in this compound want to have the same number of electrons as the noble gas, you need to account for 18 electrons. But you don't have 18 in reality. You've got 1 from hydrogen, 4 from carbon, and 5 from nitrogen. Those are the valence electrons. And so in total, you have 10. But again, the reason why we can do this is because if we take these two numbers and take the difference, okay, here, oops, and take the difference, then that's the number of bonds. And the number of electrons that we commit to those bonds happens to be 8. Those are the number of electrons that you need to commit to bonds. And of course, 8 divided by 2 means 4 bonds. So that's what we see right here. Remember, hydrogen can only have 1 bond. So the other 3 that you drew, like this is how I would do it. That's the skeleton. And then you can only have 1 bond to hydrogen, always. And then remember, we have 4 bonds, so you have to put it there. That's how you commit the 4 bonds. Then what you can do is you can figure out the remaining electrons. And the remaining electrons are going to be, we have 10, we've used 8, so that's 2. So that's 1 lone pair. And of course, this hydrogen is happy with its 2 valence electrons. This carbon is happy with its 8. This nitrogen is lacking 2 more. So that's the 8 electrons on the nitrogen, the 8 electrons on the carbon, the 2 electrons on the hydrogen. Hydrogen always prefers 2. And again, you can see that in my analysis here. Okay, my analysis here. Each time we do that, and that would be the Lewis structure for hydrogen cyanide. Hydrogen cyanide. Let's go to something more sophisticated. Let's go to something like NO minus. Remember, I told you NO violates the octet rule because nitrogen comes in with 5, oxygen comes in with 6, so that's 11. But this is not an odd number of electrons because it's NO minus. So you've got 1 extra electrons in this particular case. So again, the charge means you add 1 more electron in the total structure. Octet electron is going to be 8 and 8, that's 16. Total valence electrons going to be 5 from nitrogen, 6 from oxygen, and then 1 extra electron because of the charge. The charge means that you have 1 more extra. So you have to add 1 to that column. Don't subtract it, okay, because electrons are negatively charged. So if it's -1, you add 1. If it's -3, you add 3. Anyway, again, you get these 2 famous numbers. Those 2 numbers right there tells you the number of bonds. So we have 16 minus 12, that's 4 divided, there's 2 bonds in this structure. So the only way you're going to put 2 bonds is just draw 2 lines. In that 2 bonds, you've committed 4 electrons. So if you subtract 4 from 12, that's going to be 8 electrons remaining, or 4 lone pairs, 8 divided by 2. See how easy this becomes once you do it a number of times? It becomes almost automatic, yet it gives you the information you need to do the Lewis structure correctly. And in the quiz, if you're in my lecture, all you really need for a lot of these things are just the bond table, because the bond table gives you a lot of the information: total valence electrons, number of bonds, number of lone pairs. So let's complete this. Here's our 2 bonds, okay? 4 lone pairs like we predicted. Here they are. Because this oxygen only has 2, we need 4 more to get 8. This nitrogen only has 2 bonds or 4 electrons. It needs 4 more to have 8. So that's going to be the octet rule. It's going to obey correctly. And that's going to be our Lewis structure. You put a bracket on the, when a chemical is an ion, like in this case, it's NO minus, and then you put a bracket and then the charge outside. That's generally how you designate that, okay? But these chemicals are a little bit easier. Let's take a look at this one. Again, CH2, Br2, 1 carbon, 2 hydrogens, 2 bromines. Octet electrons, this is the atomic arrangement. Notice that I make my first element the central atom. And generally in a simple chemical, the first element is your central atom, except if it's hydrogen or fluorine. Okay. Octet electron, 8 for carbon, 8 for bromine, but there's 2 bromines. So it's 8 times 2 is 16. And then 2 for hydrogen. 2 times 2 is 4. For a total of 28. If each of these atoms had the same number of electrons as a noble gas, we would need 28. But of course, we don't have 28. We have the total valence electrons. Carbon's coming in with 4. Bromine, because it's a halogen, comes in with 7 apiece. So that's 7 times 2 is 14. And hydrogen comes in with 1, but there's 2 hydrogens. That's 2. Okay. And so 28 minus 20, that's equal to 8 electrons committed to bonding or 4 bonds. Oops. And that's easy to do right there. Okay. That's easy to do. That's 4 bonds. When you draw bonds, your first priority is to connect the atoms adjacent to each other. And then if you have other bonds to consider, okay, then go back to that table that I showed you that nitrogen prefers 3 bonds, oxygen prefers 2 bonds, and carbon prefers 4 bonds. Okay, so I'll show you an example of that later, but we've used 8 electrons from the 20. So that means we have 12 remaining electrons unaccounted for. 12 divided by 2 is 6. We've got 6 lone pairs. Okay, 6 lone pairs. And those lone pairs, of course, are going to go to bromine because it needs an octet. And now in this structure, all the atoms have an octet. Hydrogen prefers a duet, 2 electrons. Okay, and so that's what you see right there. That's what you see right there. You need to practice it so you're comfortable with it. It's a little bit work in terms of the bond table, but you get the correct answer. Okay, let's take a look at this selenium dioxide. I won't walk you through this, just kind of watch. Or that's selenium and 2 oxygens. The connectivity is selenium in the center atom, and the oxygens are surrounding it. 8 and 16, that's 24. Each atom brings in 6. 6 for selenium, it's in the oxygen family. 6 for oxygen, but there's 2 of them, that's 18. 24 minus 18, that's 6. 3 bonds. Here's what I mean by committing the extra bonds. You know that you connect these 2 first, but we have to account for 3 bonds. So you just pick either that oxygen or the other oxygen. It doesn't really matter to get your 3rd bond, but you have to draw 3 lines for 3 bonds. Okay, and that's what we see right here. And I could have easily put it in the other side, doesn't really matter. And then we use 6 from the 18 because again, this is our total valence electron. So that gives us 12. 12 divided by 2, that's 6 lone pairs. And you can see from this structure that this oxygen needs 4 more. So that's 2 from the 6. And this oxygen needs 3 more. So that's 5 total from the 6. So we need to account for 1 more lone pair. You can see that the oxygens are so satisfied with an octet. The selenium needs that last pair of electrons to give it 8. Okay, so that would be the Lewis structure for selenium dioxide. And that's basically what we have right here. Oops, sorry. Octet rule, always the driving force for completing the Lewis structure. Okay, let's take a look at this complicated chemical. This right here, I believe is diamine. It's like urea, protonated urea, okay? And again, this is a little bit more complicated in terms of structure. You have multiple central atoms, but the approach is still the same. You write the formula here, you break down the number of atoms in that formula, 2 nitrogens, 1 carbon, 1 oxygen, and 5 hydrogens, and then there's a positive charge, Don't forget that. Otherwise, you're going to get screwed up, okay? If you mess the bond table, you're going to get the wrong structure. That's the connectivity. That's the connectivity. I would give you that because it would be too difficult for you to figure it out, okay? Once you get to organic chemistry, you will see that this is what starts the chain. It's connected to that carbon's connected to that oxygen, but that carbon's also connected to that nitrogen. That's what you guys will learn in organic chemistry when you take 130. And that's basically what we have here. This nitrogen's connected to this carbon's connected to that oxygen, and this nitrogen right here. Okay, but let's complete the bond table to show you that the bond table is your answer. Octet electron. 8 for nitrogen, there's 2 of them, so that's 16. 8 for carbon, 1 of them, so that's 8. 8 for oxygen, 1 of them, so that's 8. And then 2 for hydrogen, 5 of them, so that makes 10. So you have to deal with 42 possible. 42 would be the number of electrons if each of them had the same number of electrons as a noble gas. In reality, nitrogen comes in with 5. Carbon comes in with 4. Oxygen comes in with 6, and hydrogen comes in with 1. When you multiply it against the number of atoms in that structure, you come up, and then don't forget the negative 1. Why negative 1? Because the positive means 1 less electron. So we have to take it away from this pool. We have to subtract the total 1 from the total. So when we add that up, that's 24. Now you can see 42 and 24, that's a big number. And that tells you you have to commit 9 bonds to this compound, 9 bonds. And so how do we get 9 bonds? Let's take a look. These 2 are adjacent, so you have to draw a line there. That's 2. That's 1 bond. 2 bonds, 3 bonds, 4 bonds, 5 bonds, 6 bonds, 7 bonds, 8 bonds. We need 1 more. Where do we place it? Where do we place that 8th bond? And you remember that oxygen prefers 2. Okay, oxygen prefers 2. Plus that's the only place you can put it. You can't put it here, because if you put it there, you're going to have nitrogen with 1, 2, 3, 4, 5 bonds. That would be 10 electrons. Violate the octet rule. Okay, this carbon only has 6 so far. So the best place to have it, it's right there. Oxygen now has its preferred 2, and carbon has 4, which is what we said in the beginning. That's our 9 bonds. How many lone pairs? Well, 9 represents 18 electrons. So that's 6 electrons. We haven't used up that yet, remaining electrons. And 6 divided by 2, that's 3 lone pairs. 3 lone pairs. So you can see that in this analysis right here. Okay, 3 lone pairs. And where do they go? The hydrogens are totally satisfied with 2. So don't touch the hydrogens. This carbon has 8. This carbon has 8. This nitrogen has 8. But that oxygen only has 4 from the 2 bonds. So it needs 4 more electrons to give it 8. Okay, but remember, we need 3 lone pairs. We've only used 2. This other nitrogen needs the other lone pair because right now it only has 6. So again, once you come to the end, you want to make sure that each atom has 8 hydrogens satisfied with 2. And with the bond table, you have that advantage to know how many lone pairs you're working with and how many bonds you have to have in that structure. If I count the number of lines here and the number of lone pairs, that comes up to 24. This is 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 electrons. And that has to be consistent with the total valence electrons. Okay. So again, pretty straightforward. It's an ion, so we put a bracket and a positive because that chemical has a positive charge. Here's another one, more sophisticated. I'm not even going to talk about it. I'm just going to walk you through the PowerPoint. That's, again, the arrangement. This happens to be glycol. Okay. 44, when we do total valence electrons, that's actually 26. 44 minus 26, that's 9 bonds. 9 bonds. Okay. There's your 9 bonds. Just connect them. Just connect them. 1, 2, 3, 4, 5, 6, 7, 8, 9. How many lone pairs? Well, 26 minus 18, that's 8 remaining electrons, 4 lone pairs. And where do they go? It's obvious they have to go to the oxygen. Okay, that's your Lewis structure. This is methanol. And again, I give you a lot of examples here so that you get used to it. Sorry, that's not methanol. This is tert-butanol. It's an organic compound that you guys will be studying in organic chemistry. Okay, this is tert-butanol. Notice I put the CH3 like this. I could have easily wrote carbon with hydrogens around it like that for that CH3. But when you get to organic chemistry, when you have a CH3 group, we just kind of assume that it's a carbon in the center and 3 hydrogens that are sticking out. So when we do the bond table, 60 minus 32, that's 28. 28 divided by 2, that's 14 bonds. 14 bonds. It would be really difficult for you to figure this out based on that structure. Okay, but with the bond table, you have that advantage. You have that advantage. 14 bonds. So let's see how that works. I put 9 there because you see how these things right here, that's a CH3. CH3 is actually this. And then that's going to be connected to this carbon right there. Okay, so these CH3 account for 9 bonds that you have to commit. That means that 14 minus 9, we need 5 more bonds in the structure. Okay, and those 5 bonds are going to be between these carbons right here, this carbon right here, this carbon right here, this carbon oxygen, and that hydrogen, and that's your 5. 1, 2, 3, 4, 5. So that's your structure right there for a total of 14. How many remaining electrons? Well, we take 32, subtract 28. Again, 28 because that's the number of electrons we've used up on bonding. Don't take 32 and subtract from 14. 14 is the number of bonds, but in those 14 bonds, there's 28 electrons. So 32 minus 28, that's 4 remaining electrons. Of course, those 4 remaining electrons are going to go to that oxygen. Okay, that oxygen right there. That's what you see. Okay, that's your structure. So hopefully the bond table, and we did a number of examples, shows you that it really is easy to get 1, the total valence electrons, 2, the number of bonds, 3, the lone pairs. And those things I will ask you in your quiz. Bond table gives you that right away. Bond table gives you that right away, but you have to do it correctly. With the bond table, with the Lewis structure, we now get to the most easiest part of this whole exercise, figuring out molecular geometry. It's super easy because you have a table that you can use. I don't expect you guys to memorize this, okay? You can actually use this table when you work on this activity or the quiz. So let me just show you that for this example, I'm going to do the Lewis structure. That's carbon monoxide. That's 10 total valence electrons. That's what you would put in your sheet. Oops. That's NO minus. That's 12 valence, total electrons, total valence electrons. That's what you would put in your sheet. These are the examples we just did, okay? These may not necessarily be the chemicals in your activity, but again, this is how you would fill out that worksheet, okay? Like that. So these are just filling out that worksheet with the Lewis structure and the total valence electrons. Well, here's the entire series, okay? So let's move on to molecular geometry. So the VSEPR stands for valence shell electron pair repulsion. Basically means that the electrons in the outermost orbital want to stay as far apart as possible. And the geometry is going to be dictated by these electrons staying as far apart as possible, okay? And you get a certain amount of geometry based on the skeleton. And the skeleton will be the electronic geometry. The skeleton will be the electronic geometry. That's how these things are going to be arranged in space. But the molecular geometry is going to be based on just the atoms within that chemical. You don't count electrons in its geometry, but the electrons dictate the shape that you have. So the way I like to envision it is you have the central atom, and the central atom is like a hub. Hub is right in the center of this wheel. It's like the hub on a bicycle wheel, okay? That's where you put the central atom. And then the atoms that are attached to that central atom are like the rim in this bicycle wheel. And when there's a bond that's attached to that atom, we call that a spoke, or regions of electron density, or domains, electron domains. So these things have three ways that I refer to it. I can call it a spoke. I can call it a region of electron density. Or some book calls this electron domain. So when you have a bond pointing to one atom, that's an electron domain. When you have multiple bonds pointing to a single atom, multiple bonds like a double bond, triple bond pointing to a single atom, that counts as one domain, okay? One domain. So in this example that I have right now, that you see two domains, two regions of electron density, two spokes. Even though this is a triple bond, it's pointing in one direction. So that counts as a single domain, single region of electron density, single very strong spoke, okay? And then electron pair, lone pair, acts as its own domain. It's a region out there. And the reason why we do that is because these regions of electron density dictates the shape of the chemical. These things want to stay as far apart as possible, so they take on a geometry that allows them to be as far apart as possible, okay? And those geometry happens to be, well, here are examples that we just did in the previous discussion. These are Lewis structure. And what I want to illustrate here is this does not have a central atom. Let me change my pen here. This does not have a central atom. There's only two atoms there, and it's going to be in a linear fashion. They're going to be next to each other. No matter how they twist, it's always going to be linear. Okay, so that's always going to be a linear geometry when there's only two atoms involved. Okay, this two atoms, linear. No, there's no doubt. But now we have atoms where we have more than two, and there's a central atom. So we're going to figure out the geometry based on the central atom. We're going to figure out the geometry based on that central atom, the geometry around that central atom, that central atom, that central atom, that central atom, and this central atom. This has 2 central atoms. This has 1, 2, 3, 4 central atoms. And the geometry that we're going to use is going to be based on the VSEPR rule. Okay, so this is basically it. I think this might be found in your textbook. This is what I like to use. This is found in your lab manual. And what you want to do is you want to start here. That right there is electron domain or regions of electron density. Or spokes from central atom. And it's only going to be 2, 3, or 4. Why is it only going to be 2, 3, and 4? Because we're limited by 8 electrons. So the geometry that we're going to be dealing with is going to be 2 electrons or 2 regions of electron density from the center, 3 regions of electron density from the center, or 4. It makes it easy. It makes it easy. Okay, so whenever you have 2 regions coming out, then the electronic geometry is always linear, and the electronic designation is AE2. E stands for lone pairs or regions of electron density. There's 2 regions of electron density, AE2. The skeleton is going to be linear. When there's 3 regions of electron density, we call it AE3. And the best way to keep those regions as far apart as possible is to be a trigonal planar. These things are 120 degrees apart. Trigonal planar. And when we have 4, then we have to use the 4th dimension. This is called tetrahedral. We call that AE4. And this is about 109.5 degrees, that angle. But that's not the molecular geometry. That's just the skeleton, the electronic geometry. The molecular geometry depends on the atom that is in your structure. So when you have a linear, when you have a linear electronic geometry and the ends actually have bonded atoms, then the molecular geometry is also linear. When you have 3 regions of electron density, all 3 at the ends could be bonded atom, or only 2 at the ends can be bonded atom and 1 lone pair. So that's what we mean by these numbers right here. Okay, when we have 4, you can have 4 bonded atoms at the end, like you see right here, or 3 bonded atoms and 1 lone pair, or 2 bonded atoms and 2 lone pairs. So when you get to this point, you can just use this chart to figure out first your electronic geometry, molecular geometry, and its designation. You want to use this chart. It makes it easier. So let's take a look at the linear configuration. Carbon dioxide is linear. Why? There's 2 regions of electron density around that. Again, pay attention to the central atom, always the central atom. Don't be looking for geometries around that oxygen. That's dangling off to the side. It's not going to dictate what's around it. It's only the central atom. So don't count lone pairs on the oxygen. You only want to count regions of electron density around the central atom. And the central atom in this case is carbon. And there's 2 regions of electron density, albeit each region has 2 bonds, but it's pointing in one direction right here. That's your electronic geometry, therefore, is linear. And at the end of these 2 are atoms. Your molecular geometry is also linear. This is also linear. Your molecular geometry. Okay. Another example is BeH2. 2 regions of electron density, linear electronic geometry, linear molecular geometry. So look at this guy, this hydrogen cyanide. 2 regions of electron density, 1, 2. Don't get fooled by that lone pair. That's not a central atom. This is the central atom. You're only paying attention to central atoms. So how many regions coming out. How many spokes are coming out of that hub? 2, albeit one of them is a triple bond, but that's still a single region. 2 regions, that's this right here. It's linear. It's linear. Okay. So carbon monoxide is linear. NO minus is linear. There's only 2 atoms. Whenever you have 2 atoms, it's always linear. But when you have 3, then you have to see that indeed it's 2 regions of electron density. Let's take a look at a more complicated scenario. 3 regions of electron density. When you have 3 regions of electron density, like in BH3, again, 1, 2, 3, then we have a trigonal electronic geometry. Again, just use that chart. Don't overthink it. And then at the end of BH3, there's bonded atoms. There's a bonded atom here. There's a bonded atom here. There's a bonded atom here. So the molecular geometry is also trigonoplanar. Trigonoplanar right here. 3 bonded atoms, 0 lone pairs. It's trigonoplanar, and the molecular geometry designation is AB3. B stands for bonded atom. A stands for the central atom. Look at NO2 minus. NO2 minus is this guy right here, and you can count 1 region, 2 region, 3 region. A lone pair is its own region, 3 regions. So again, we're going to be using that. Trigonoelectronic geometry. Trigonoelectronic geometry. At the end of these domains, only 2 of them are bonded atom. 1 of them is a lone pair. So you go from here down to here because you have 2 bonded atoms, 1 lone pair. The geometry around that nitrogen is bent. Because when you look at this chemical, what you will see is this right here, a bent structure. You don't see electrons, but the electrons here are actually pushing down on that oxygen to make it bend, okay? So that's why the overall molecular geometry is bent, because the skeleton is trigonoplanar. So that's a bent molecular geometry. And you can see it right here. You're only looking at atoms when you have the molecular geometry. Yeah, the electrons are there. It dictates the shape, but you don't look at, you can't see that with an X-ray results, okay? When you actually analyze the chemical, you don't see the electrons. You only see the atoms, and the atoms are bent. Here's another example of trigonoplanar, BF3. The carbon in this guy, this is urea, is trigonoplanar. 3 regions of electron density, 1, 2, 3. At the end, it's bonded to nitrogen, it's bonded to oxygen, it's bonded to nitrogen. At the end, it's bonded atoms. Likewise for that. That, however, is not trigonoplanar molecular geometry. Let me erase that. But you can see the 3 regions of electron density. 1, 2, 3. 2 of them are bonded atom. 1 of them is a lone pair. That guy's a bent structure. That's a bent structure. Use this bond table. Let's take a look at 4. 4, now there's 3 possibilities. One in which at the end of all of these, you've got bonded atoms, like in methane, or only 3 of these 4s have bonded atoms. The last is a lone pair, like in ammonia, or only 2 of these at the end are bonded atoms and 2 lone pairs. It's still 4 regions of electron density, but now you have 2 bonded atoms and 2 lone pairs. You would go right here. And so when you look at water, because you don't see the electrons, it's actually a bent structure. This is the water molecule. It's actually a bent structure, okay? Even though the electronic geometry is tetrahedral. So let's take a look at this. This right here has 4 regions of electron density. So it's going to be here. Its electronic geometry is tetrahedral, but because it only has 2 bonded atoms at the end and 2 lone pairs, that's going to be bent around that oxygen. But these carbons right here have 4 regions of electron density, and at the end of these bonds, they have bonded atoms. So they're going to be tetrahedral. So again, you have 2 geometries when atoms have 2 central atoms. If it has more than 2, then that's how many geometry you indicate. And around each atom, there's a geometry, and when you put it all together, it looks very weird, but that's the geometry around each atom. Okay. Likewise here, you actually have 3 types of atoms. The round around the carbon, that's 4 regions of electron density. That's tetrahedral, both in the electronic and the molecular. This likewise also have 4 regions of electron density. This has 2 regions of electron density. Sorry, 4 regions of electron density. 2 are bonded atoms. 2 are lone pairs. So that's going to be a bent around that oxygen. It's going to be bent around that oxygen. So this is a more detailed table that you guys will use. And over here, it tells you what the bond angles are. And then we also have something called the hybridization. The hybridization is what atomic orbitals make up these orbitals that you have in your geometry. You don't have to know more than that. Know that if it's tetrahedral, it's sp3. When it's tetrahedral electronic geometry, it's always sp3. When it's trigonal electronic geometry, it's always sp2. And when it's linear, it's always sp. The S stands for the s orbital, the P stands for the p orbital. Remember, there are 3 types of p orbitals. So that's why you can get sp3, sp2, and sp. Don't overanalyze that. It's associated with the electronic geometry. So let's do an example in one of these so that you can see how it works. So I'm going to share my screen here with one of the examples. Let's take a look at this one, OF2. Okay, OF2, if you, OF2, again, to show you how simple this is, 2 fluorines, octet electrons, total valence electrons. This is going to be 8. This is going to be 2 times 8. That's 16. That's a total of 24. Oxygen actually brings in 6. Fluorine brings in 7 times 2. That's 14. 14 plus 6 is 20. 24 minus 20, that's 4 electrons committed to bonding. 4 divided by 2, that's 2 bonds. Of the 20 electrons that I have in this total valence electrons, I use 4 for bonds. So I have 16 remaining electrons. So 16 divided by 2, that's 8 lone pairs. Okay, so let's draw the Lewis structure. Oxygen's the center. Fluorine cannot be the center. The fluorine flanks it. We commit 2 bonds. There we have, those are 4 electrons. And then we need 8 lone pairs. 1, 2, 3, 4, 5, 6. Okay, 6 electrons, 3 lone pairs. 1, 2, 3, 4, 5, 6. Now each fluorine has an octet. But we've only used 6 lone pairs of our total 8. The other 2 has to go on that oxygen. Now each has an octet. Now we look at this central atom and we look at the number of domains. We have, let me change my pen here. 1 region, 2 regions, 3 regions, 4 regions of electron density. So we go to our table, and in our table, we see that 4 gives us tetrahedral. Okay. And then in the tetrahedral, we go to the bottom, there's 2 bonds, bonded atoms, and 2 lone pairs. So it's going to be bent. And that's what you would write down. You would write down bent. And so if you go to your activity, then you can see that for oxygen difluoride, the number 1 is which structure? We came up with that, A. So you put A right here. The right, the total valence electrons, we calculated that as 20. So we put 20 right here. The AE designation is AE4. And you know that because we have 4 regions of electron density, tetrahedral AE4, 2 bonded atom, 2 lone pairs. So our molecular geometry is bent, AB2E2, 109.5. So those are our answers here. AE4, tetrahedral, and for number 5, we're looking at that shape, tetrahedral. For number 6, what we have is type of designation. We said it was AB2E2 right here. You want to type that in. Molecular geometry, we said it was bent tetrahedral because the skeleton is tetrahedral. It's different from bent trigonal. And that would be this right here, bent. And then the approximate bond angle, go over here and you can see that bent tetrahedral, it's about 109.5. So that's what you want to write down over here, about 109.5. And then you're done. It's pretty easy once you get the hang of it. So that is your activity. Let me finally finish up with this. Let's go to this page right here. Okay. Bond length, bond angle, partial charge, bond dipole. And again, if this thing gets squished like this, so you don't see it all, you need to either scroll down or expand your window so you can see it. But this is just a screenshot. You guys will need to put this on your paper and then upload it. So let's, like I said, let's do carbon disulfide, because I know that one of you wasn't here early on. So you just want to click on this link right here. And when you get to that link, you want to go to Chemdl. The other one's a lot more sophisticated. And then right here, you just want to type in carbon disulfide. And when you do that, it actually will take you to, and you have to spell it correctly. Or maybe you put in the correct formula right there, okay? Put in the formula or you do the name, and it's this compound right here, carbon disulfide. Notice it's very similar to carbon dioxide. Why? Because sulfur and oxygen are in the same family. So the molecular geometries are going to be identical and the Lewis structure are going to be identical. But now that we have it here, let's see what the questions are asked. We want to know the bond angle, the bond length, the partial charge, the molecular geometry, and the bond dipole. And we can answer that all here. We want to know the bond length. Click on that. Now you can see the bond length. They're 1.157 nanometers. You want to write that down. You want to see the bond angle right here. It's 180, but you knew that already. Let's click that and let's look at the partial charge. Around the oxygen, it's 0.26. On the carbon, it's 0.52. Let's turn that off. Where's the bond dipole? The bond dipole is that right there. And it's pointing away from the carbon. You have to sort of draw that. And that is your activity. That's your activity right there. Okay. So you guys have any questions? I think it's pretty straightforward, but try and do this if you can before you take the quiz this weekend. If you are in my lecture, it'll give you a lot of practice. It'll give you a lot of practice. Okay. But that's all I have to say for this activity. It's pretty straightforward. If you spend a little time with me understanding Lewis structure and valence shell electron pair repulsion. If you have to learn it on your own, you're going to scratch your head and wonder what's going on, because it can be very intricate and confusing. Okay. Anyway, 7:30. So appreciate you guys hanging out, and thanks for attending.